And the very last thing I want to do, because we'll get into more about isomers in the next class, but it's just the orbital hybridization. And that's just, once again, I'm just going to draw. So there's a double bond. And if we pointed that one, why won't it let me here? Versus the terminal one. Okay. And so the terminal one, first of all, what shape is that terminal one? There's a carbon in a single bond, so therefore it's what? It's tetrahedral. And so what's its orbital hybridization? It's sp and then 3. Okay. Whereas if it's in a double bond, what's its shape going to be? It's, pardon? Trigonal planar, okay, and its orbital hybridization would be, and it won't let me, there we go, so sp2, yep, so it's just, come on now, you can do it, gotta have like positive self-affirmation. All right, and so that's where we'll end class for today. All right, so I'm just now going to pick up where we left off, and we were talking about the isomers, and in particular, so far we've only discussed stereoisomers, cis and trans, but there are other types of isomers that are possible. And unfortunately, I put my notes down in the wrong order. Okay, and so what happens? So we've talked about, I'm just going to use butene, like the possibilities of butene, because the fact is that there's, if you do one that's larger, there's many, many more possibilities. But with the different butenes, we have, well, first of all, if you have one butene, 1, 2, 3, 4, there's no stereoisomers that are possible, okay? Because the reason being is that one side only has hydrogens on it. One of the carbon only touches hydrogens besides it having double bonds with the second carbon. Whereas we've already discussed what happens with 2-butene. We can either have the cis or we have the trans. Okay, so that's nothing new. And of these two, as we just mentioned before, the trans would be more stable due to steric interactions. That would be less favorable on the cis than on the trans. The two methyl groups, the larger groups are further apart than they would be in the cis. But what happens if we have more than 2 groups? We have to be able to differentiate between the 2 isomers if there's more than 2 groups there. And table 5.1 has rules for priority. And that'll make more sense in just a moment. So let's say, for example, and I'm going to draw it all the way out for these 2, maybe. CL, BR, H. Okay, so there's one of them. And then let's draw the stereoisomer for this. To draw it, you just switch what's on the top and the bottom on one carbon. If you switch them on both carbons, it's the exact same compound. But you just switch on one. So I'm just going to switch the chlorine and the bromine, and I'll put it in a different color so that way it's easier to see. Tell the difference. So now the bromine is on top, the chlorine is on bottom. Okay, so these are the 2 possibilities, and they could very well have different properties, and we have to be able to differentiate them in their naming. Okay, but we can't do the same way with cis and trans. We can't do cis and trans because there's more than two non-hydrogen substituents. So there's another naming way that they do this, and it's called the E and Z or E and Z, and I'll explain the reason why in just a moment. But because of this, you have to give priority. So you look at each carbon. So first off, I'll look at this carbon, and we have to say which one has more priority. The chlorine, oh, whoops, hit the wrong button. The chlorine or the bromine. And so what you do is you go down, I'm sure that the way that they do it in the table, it's been a while since I looked at it, they say first you look at the atomic number. Whichever one has the higher atomic number will have the higher priority. But you also look at atomic mass, because if you have a carbon-13 versus a carbon-12, carbon-12 is the main one, but carbon-13 is the one that's radioactive, you know? Carbon-13 gets top priority over carbon-12. And so you can just always think that the atomic mass trumps everything. So, because atomic number and atomic mass are, interrelated. Those that have a higher atomic number will have a higher atomic mass. So between chlorine and bromine, which one has the higher atomic number? Which one's further down on the periodic table? Bromine. And so it gets high priority. And so I'll do that in a different color. Let's see, let me just change the colors here. So it gets high priority. This gets a low priority. Now, if we look at the other carbon, we don't have that luxury. The first thing that they both touch, this carbon first touches a carbon that has two hydrogens. This side, it's a carbon with two hydrogens. So what you do is you keep going down the line until you see the first difference, and you say which one's got the higher atomic mass or higher atomic number. And so here we go from a carbon with two hydrogens. The next atom is an oxygen or a carbon. Which one of those is going to get top priority? The oxygen. And so it's a high, low. And now I'm going to go on the other side and do the same thing. Of course, bromine we already said was high, chlorine was low, the oxygen was high, and the carbon was low. Also, you look at the number of bonds. I don't have an example here, but like a double bond is a higher priority than a single bond. So a carbon-carbon double bond versus a carbon-carbon single bond. The carbon-carbon double bond will be higher, or a carbon-carbon triple bond. Likewise, an aldehyde would trump an alcohol, because an aldehyde is making two bonds to the same oxygen, whereas an alcohol makes one bond. Carboxylic acid would trump an aldehyde. So hopefully you're kind of getting some of the ideas that you just keep going down the line until you see that first difference and say which one. And I'll do some other examples. Salud. Okay, so, go zoom tight. All right, so now we have to know, we've prioritized these, but now we've got to give them their actual names. And the names, one of them gets E configuration, and one of them gets the Z or Z configuration. And pardon? Okay, just a second. Okay, so the E configuration stands for, and I'm going to have to type this one out. Entgegen, which I'm sure everybody knows what that word means. It's German, those crazy Germans, and that means opposite. And we lost it once again. Just remember, the Entgegen means opposite and that's the one that they just call E. Usually they put the E in italics. I don't expect you to try to draw it in italics, but you would just say E and then you would name it accordingly. Okay, let me just hit enter before we see. I think that what's happening is, well now, first it was the iPad that lost the signal, now it's the see what Wi-Fi we can get. All right, so Entgegen meant opposite. The Z one stands for zusammen. I'm going to spell it for you. telling you, it's the Germans won on this on this front. They were not kind to my people. And Zusammen stands for together. Okay, so that's why there's this called the E and Z. And so this one right here is the E configuration. This one is Z. Okay, and actually this one you possibly could, name, but I wouldn't ask you to name this one at this point. However, they only contain carbons, hydrogens, halogens, oxygen, things like that. I could ask you to name something, and we'll give some examples later. And if I ever say you have to include stereochemistry, this is just another form of stereochemistry. Just like cis and trans, you just have to remember that if it's got more than 2 non-hydrogen groups hanging off of it, you can't use cis and trans, you have to use E and Z. Okay, so let's just do one other example. There we go. I'll give you a moment to draw it, and then we'll just have to figure out if it's the E or if it's the Z. Why did they, the new iTunes automatically comes with some music on it.
Isn't it like a U2?
It's U2 and everything, and I think that because it's iTunes, it's trying to buy something else. And this isn't my computer, this is a loaner. All right, so now we have to determine, let's start on the left-hand side. Which is going to get top priority? The high priority, is it going to be the thing that's on the top or the thing that's on the bottom?
Top.
The top, and the reason being is we just go down the order. We have a CH2, a CH3 versus a CH2. So this one, if I draw it out a little differently, it's going to look like this. Whoops, that's not what I was going to do. But this carbon right here is touching a it's touching a hydrogen, and a carbon, whereas its counterpart there is touching just 3 hydrogens. So that third hydrogen is a lower priority than the third carbon. And so that's why this gets the high priority and this one gets the low. So now if we go to the right-hand side, which is going to get the high priority? The thing on the top or the thing on the bottom? Does everybody agree? Does someone disagree? It's the bottom. I know, just blew your mind. And so, why is it the bottom?
Because alcohol comes first.
So you go, whoa, you don't do that. You go down the line. So the very first thing it touches, there's a carbon that has 2 hydrogens and a carbon. But this first carbon is touching an oxygen. And so the first difference is an alcohol versus 2 hydrogens. And so the oxygen trumps that. So that's why I deliberately put one up there that's more difficult. And so this would be, is this E or this Z? This one's the E. Okay. Now we're going to learn there are 2 major ways to make alkenes. You do need to know these mechanisms and the conditions. We're going to see this over and over and over again. And I looked, the typing program here doesn't have beta, but this is called beta elimination. So there, that's a beta elimination. So the 2 ways are dehydration of alcohols. I'll show you what that means in just a moment. And like a great Jeopardy vocabulary word, dehydrohalogenation of what does RX mean? And it's not prescription. Pardon? Alkyl halides. Okay. All right, so these are the two broad ways. I really need a bigger desk up here. So I'm just going to do the general reaction, and we'll talk about the mechanisms, because each one of those ways has two mechanisms. It's the same thing. It's just what you start off with, and the conditions are a little different. So the general reaction for the alcohol is as follows. You have to have a vicinal, well, you have to have an alcohol. First of all, even though I don't mean it to be a trick question, your starting compound has to have at least 2 carbons. Sometimes they'll put like methanol up there, because there's another type of reaction that alcohols can end to do, and it's amazing the number of times that people say that will forget and have it making an alkene, but methanol doesn't work because it's only got 1 carbon. So you have to have at least 2 carbons. Okay, and the neighboring carbon, which is called the vicinal carbon, the next carbon next door has to have at least 1 hydrogen. If it has no hydrogens, you cannot do a beta elimination. You always have to have a hydrogen on the vicinal carbon. The other 2 things can be anything else. Okay, that may affect reactivity, but this is the minimum. And if it's a dehydration, what do you suppose is leaving? Water. And so if you look here, we've got an OH, and then we'll have this, and then we'll have an H, but it's not necessarily that one. It's going to be the leaving group. And so the reaction conditions for alcohols is that it's acid catalyzed. So you have to have an acid around, so a proton donor. Okay, it's not that way with alkyl halides. It's base catalyzed. But with alcohols, usually you're going to find out, this is true for many of the reactions with alcohols, is it's going to be acid catalyzed usually. And then the final product here, of course, is going to be the alkene in water, because it's a dehydration reaction. Whereas if it's a dehydrohalogenation reaction, I'm just going to do the general overall reaction first. I thought that was ours for a second. I was like, don't do that to me. So if it's a dehydrohalogenation of an so that means we have to start off with an alkyl halide. And once again, the vicinal carbon must have at least 1 hydrogen. I kind of already gave this away. It is not acid catalyzed. It will not work if there's an acid around. It's base catalyzed, which I'm just going to draw the base like this. But some of the bases that are used, alkoxides, are wonderful bases that are used, and I'll explain what that is in a moment. Hydroxide it's borderline for how well it works. There's one called amide anion. It's really good. It's a strong base. But you'll see what I mean whenever we go through examples. And this has to be a base. And so we're going to get our alkene. What's the other product? If it's a dehydrohalogenation, what's the inorganic product? So, right. So it's going to be like hydrochloric acid, hydroboric acid. It's HX. That's the reason why if you put this in acidic conditions, it won't work, because you're making an acid as a product. So if you think back to the Schottler's principle, it would favor, we're going to find out it can go backwards with an alkene to make an alkyl halide, but it can't go frontwards very well, or at all. So, okay, so those are just the general ways. Now we're going to actually do some of the real mechanisms. So, before we get started there, I have my rule of thumb, and they don't have thumbs. And the little emoticons. And this should just be review of the rule of thumb, but anytime that you have two or more possible intermediates or products, you want to choose the more, or most, if there's more than two, stable as the major intermediate or product. This is especially true whenever we're making alkenes, because we've already talked about how you can make more than one possibility. You know, you can have cis versus trans, you can have, E versus Z, but we're going to find out that there's even more possibilities there. And so stereoselectivity is the easiest to talk about because that one's E versus Z, or in particular, especially cis versus trans. That's the one you see the, whoops, that's supposed to be trans, not tran, but I ran out of room. Regioselectivity is a little bit more difficult. So I'm actually going to put in a new slide because I'm going to need more room. But whenever we say regio for selectivity, it just means it selects one over the other. But what does regio kind of sound like?
Region.
Region, and that's actually what it is. And so I'll show an example, just a moment, for regioselectivity. Okay, so here, let's draw this. And of course we have to have an acid, an space acid, not antacid, because that's actually a base. Okay, so I just wanted to specify that. I'm just going to use sulfuric acid, and many times you want to add heat. So we'll say like 80 degrees or 100 degrees. 100 seems to be the magic number many times, but so it's hot. There are actually two possible, even if we don't start talking, well, we'll find out whether or not there's like cis versus trans, but there are two possible regio products. I know that because what you do is this is the ground zero carbon, the one that contains the alcohol. How many neighboring carbons does it have that has at least one hydrogen on it? 3. How many of them are chemically non-equivalent? 2. So what we're saying is these two are the same, right? They're both methyl groups, so this one's different. So we have this type and we have this type. So I'm going to draw both of those products out. I'll do it in two different colors. If it reacts with one of these types, you get that. This is going to be the alkene. Let's see, 1, 2, 3, 4. 1, 2, 3, 4. 1. It's going to count carbons 1 and 2, 3 and 4. So, boom, boom. That's what it's going to look like. Here, let me erase it because I didn't. I'm going to redraw it, don't worry. It's going to look like this. That's between carbons 1 and 2. We have a methyl group, 3 and 4. There we go.
Okay.
If it reacts with the ethyl side, the other side, I'll put it in a different color. This is what the product's going to look like. Whoops, I drew one too many. Okay. And I would expect you to be able to name these at this point. My question is, which one of these is going to be the major product? And it's really major. It's 90% one of those and 10% the other. Is that the top one or the bottom one? The bottom one? Okay, and why? Well, it's more stable. That's the Miss America question. That's why I said, when I said, which one is the major and the minor? Which and why? It says, oh, it's more stable. That's like world peace. But why is it more stable?
Is it because of the hyperconjugation induction? Because
Right.
the double bonds in the middle, so they.
Right. It's more highly substituted, right? And so there is more hyperconjugation induction, or it's more highly substituted, versus the other one only has one friend to help it out. The one on the bottom, which I forgot what color you said it was, has 3 friends to help it out. And so it is the major one. This one is, oh, I keep doing that. This one is the major. The other one is the minor. And like I said, it's like 90% that one, 10% of the minor. And I would expect you to be able to name this. Now we can name one of them together. Let's name the major one, which unfortunately, let's see, I didn't name it on mine. Okay, so what will its name be?
Which one? We're naming the major?
The major, 2-methyl.
And then 2-butene? 2-butene?
Yes, 2-butene. Oh, not but-ene. Stupid autocorrect. Butene. There we go. Okay, and you don't have to worry about EZ or cis trans because we can't do that because the methyls are the same on hanging off that one carbon. So it's not 2 different things hang off of both carbons. Okay. And then, by the way, the other one is going to be 2-methyl-1-butene.
So for example, if we were to have an alkyl halide hanging off one of those edges, that hydrogen or that acid is always going to react with the alcohol group.
Right, because you can't protonate in a halogen. Because it would be positively charged. Whereas the alcohol, we're going to go over the mechanism. We're going to start it today, but we won't probably finish it until Wednesday. But we've seen that before. In fact, we'll start the mechanism now. And so there are 2, we're going to do the alcohols. So this is the mechanism. Technically, it's called E1 mechanism. This is an E1 mechanism. And I'll explain, there is a reason why it's called that. Technically, it's an E1, dehydration, and so it's very similar to something called an SN1, which we have a whole chapter on substitution reactions later on. And I do want you to know these mechanisms. If we're doing the E1 beta elimination reaction of alcohols, it's going to be acid catalyzed. And we're going to work with alcohols first. Okay, so I'm going to do one that's relatively simple. That way we don't have to worry about all the different possibilities. So let's work with 2-propanol. And we have our acid. We've actually seen this first step on multiple times. Anytime, this is another rule of thumb, anytime you see an acid, what do? It's just one word. Protonate. I mean, it can be like a mantra. Anytime, that's what acids do. You see an acid, protonate. So you see an acid, you protonate. So what can be protonated in this first step here? Just the alcohol. In fact, it's only the oxygen. You can't protonate a carbon that's already got 4 bonds. Otherwise, it becomes a carbocation, and it doesn't work. I'm sorry, it wouldn't be a carbocation. It would be a carbanion technically, because it would have 5 bonds around it, and it would actually have too many electrons. Okay, and we always go from the thing that is electron rich to whatever's electron poor. The alcohol oxygen is what has the extra electrons. and it's going to go and swipe that lowest hanging fruit. I'm going to not say the other part that the guy at UMBC would always say, but the lowest hanging fruit. And what's the lowest hanging fruit here?
One of the hydrogens.
One of the hydrogens of the acid, because that's what acids do, they protonate. And so then the electrons that were holding, that had been holding that hydrogen to the oxygen stays with the oxygen. That's why this is always fast. Some people forgot to put that in. It's fast. It's a protonation step. It's reversible. And so we are now, I'm going to draw what we have. We have this protonated, called an alkyl oxonium ion, which sounds really cool, oxonium. But remember the IUM part just means it's positively charged. I'm trying to keep this color coordinated, but I can't guarantee that it always will be. And we're left with the water. Okay. The second step is the rate limiting step, and that's the formation of the carbocation. And so, if you look, this HOH of the alkyl oxonium ion looks an awful lot like water. And so water is a leaving group. And so what happens here is the water leaves, but it takes the electrons with it. And so that's why this is the slow step, or the rate limiting step. And we are left with the carbocation. Not every alcohol can do this mechanism. This works best with tertiary alcohols and then some secondary alcohols. We're going to find out secondary alcohols can go the other way as well. But primary alcohols cannot do this. And we'll talk about the reason why later on Wednesday.
Is that a reversible step?
Pardon?
Is that a reversible step?
Well, technically it would be. Technically it's going to favor going backwards. So that's why I've got it going as a slow step. But yeah, technically it's going to be favoring this way. Whoops, wrong color I think. But under acidic conditions, yeah, it's definitely going to be a slow step. Okay. So we're going to be making an alkene. I'm going to go ahead and I'm just going to draw one hydrogen in. Remember, there's 3 on the neighboring carbon. And it doesn't, and one of the reasons why I picked this compound is it doesn't matter which carbon we look at, they're the same. I'm only drawing one in because that's the one that's going to be attacked. But we have water left. Well, technically we've had 2 waters leave, right? We had the one that left had been the alcohol, and then we had the one that was the acid to begin with. I said this is acid catalyzed, so that means you got to get your acid back. So how can we get our acid back? Acid looks like H3O plus, and we have a water, so what does that water need to grab? The hydrogen. And so the water, one of the waters, doesn't matter which one, grabs that vicinal hydrogen. But the electrons don't go with the hydrogen, because otherwise that oxygen would have too many electrons. Instead, these 2 electrons that have been holding that hydrogen go towards whatever is positive or delta plus, so it goes to form the new double bond. This is a fast, irreversible step. Okay, so it's fast, essentially irreversible, and we're left with propene. And technically we got our acid back. So sometimes I'll even draw it this way, especially in biochemistry. They like to draw lots of arrows. And I would expect you to know how to name that one because it's just propene. You could say 1 propene, but there's only one way to make propene. Because you can never have 2 propene. Okay, and so at this point, I'm going to go ahead and I'll